Okay, at the end of part 3, we learned that the only way to find the distances to stars is by something called geometric stellar parallax. Geometric stellar parallax is a way of determining depth perception. That's a big problem in astronomy because you look up into the sky and you can't obviously tell how far away stars are. In fact, in ancient times, people thought that all the stars were pretty much at the same distance and they were pasted to a giant inside of a globe called the celestial sphere. We know now that that's not the case, of course, but it was really only up until the mid-1800s that we were finally able to measure the actual distance of a star. This method is similar to what your eyes use to estimate depth. If you hold your finger up in front of your face and you blink your eyes, one and then the other, you will see your finger jump back and forth, okay, against the background of the wall. If you put it farther away and you blink your eyes back and forth, you will see it jump less. Okay, that's the very simple principle that this is based on. If you have a star that's close by, you will have a large jump in its position compared to the very, very distant backdrop of very, very distant stars. And if you find that it's jumping less, that means it's not, that it's farther away. Okay, so the more it jumps, the closer it is. The less it jumps, the farther it is. Okay. Now, once we know distance, we can adjust for the fact that light gets dimmer with distance to find luminosity. But there's another way that astronomers use to describe intrinsic brightness, and that is referring to the magnitude system. The magnitude system is, of course, a ranking system that was invented by Hipparchus about 100 BC, and it's a system that astronomers use. It's a very weird, complicated system. It's sort of backwards because the smaller the number is, the brighter the star is, and it's a logarithmic system because every difference of one magnitude is a factor of approximately 2.5 times in brightness. So, this, however, is called absolute magnitude. Okay, it's just an alternative way of describing intrinsic brightness, how bright the star actually is. It's defined as the apparent magnitude a star would have if it were at a standard distance of 10 parsecs. So what we basically do is we artificially take all the stars that we know the distance to and we adjust them, either make them farther or closer in our minds or mathematically, as if they were at a distance of 10 parsecs. And if they were all at that equal distance, how bright would they look in terms of their magnitude? So it basically compares the brightness of the stars using the magnitude system as if they were all equidistant. So this actually makes the numbers a little more manageable, and that's why astronomers use it. Well, that's one of the reasons astronomers use it. They also use it because, well, they're stubborn, and also because they like the system of magnitude, even though no one else does. But the brightest stars in the sky, the brightest stars in our galaxy, have a magnitude of around -8. The dimmest stars have a magnitude of about +15. And again, the magnitude system is weird because -8 is actually about 1 billion times brighter than +15. So it's very, very strange. If our sun was pushed to a distance of 10 parsecs, we would barely be able to see it on a dark night with our unaided eye. Our sun's magnitude would be almost 5, so it would be a magnitude 4.78. That's about as dim as the dimmer stars in the handle of the Little Dipper. And if you've ever seen the handle of the Little Dipper, you know that that is fairly dim. You need a good dark night to see the Little Dipper's handle. But luminosity and absolute magnitude are relatable. Okay, so for example, this chart here shows a good rule of thumb. The sun has 1 solar luminosity. Okay, so it's as bright as 1 sun, or any star that's 1 solar luminosity would have an absolute magnitude of approximately +5. Okay, we're not gonna deal with little decimals here. But so, good rule of thumb, 1 solar luminosity is a +5. 100 solar luminosities would be a 0 absolute magnitude. and 10,000 solar luminosities would be a -5 magnitude. And that's because a difference of 5 magnitudes is a factor of 100 times the brightness. So that means a 0 star is 100 times brighter than a +5, and a -5 is 100 times brighter than a 0, and a -5 would be 100 times 100, or 10,000 times brighter than a +5. Okay? So, to directly find either luminosity or absolute magnitude, you of course have to know the star's distance. And we find that again with geometric parallax. Once we do find the geometric parallax and we find the distance in parsecs, we use this handy but scary looking equation to figure out the absolute magnitude. So the relationship between the star's apparent and absolute magnitudes, apparent just means how bright it looks in the sky in terms of its magnitude. Absolute magnitude is how bright it would appear if it were at 10 parsecs. And it's related, those two quantities are related to each other by the distance modulus formula, which sounds extremely complicated and even has a logarithm in it, but it's really, really not that tough. Okay, all it's saying is the difference between the two magnitudes, the apparent, the one you see, and the absolute, the one that it is related by this equation, -5 plus 5 times the log base 10 of d. d is the distance to the star in parsecs. Okay, little m is the apparent magnitude, big M is the absolute magnitude. So if you're looking for the absolute magnitude, if you find the distance first, that means you know d, you know m, because we can always measure m. We can always look in the sky and measure how bright the star looks. And so if you know d, you can do a teeny tiny bit of algebra and figure out big M, okay, the absolute magnitude. And then you can go back to this chart that we see on the previous page. Once you know the absolute magnitude, you can figure out the luminosity. All right? So, now if you're not familiar with base 10 logarithms, don't worry too much. All you basically need is a calculator to tell you what it is. If you happen to have a number that is a perfect power of 10, like 1,000, the log base 10 of 1,000 is going to be 3. That's because 10 to the 3 is 1,000. So basically the logarithm, base 10, is the exponent to which you raise 10 to get that number. Okay, so for example, a log of 100 would be 2, a log of 1,000 would be 3, a log of 10,000 would be 4, and so on. Now, the hard part is the numbers in between. A log of 100 is going to be somewhere between 2 and 3, but the only way I know of very easily to figure that out is to have a calculator that has a log base 10 button on it. Okay, so little m is always known. If we find d using parallax, we can calculate m. So basically, this is an equation with 3 variables. If we know 2 of them, m and d, we can find capital M, the absolute magnitude. And that's the way it is usually used. Occasionally, it can be used in the other way. It can be used where we find the apparent magnitude of a star, and then by classification or other means, spectroscopic means, we estimate its absolute magnitude, and then we can estimate its distance. So there's another way of doing that, but we're not going to be using that all that much. Now, in the 1990s, the Hipparcos satellite obtained accurate parallaxes for hundreds of thousands of stars. When I first started teaching this course in the 90s, there were a few thousand stars that the distance was known for with absolute magnitude. This has vastly expanded the number of stars that we know the intrinsic brightness of. And within the next few years, in the late 20-teens, we will know the distance to virtually every star on this side of our galaxy because of a mission called the Gaia mission. The Gaia mission is Hipparcos on steroids, basically. It is the Hipparcos mission with insanely good accuracy. It can actually measure stars all the way to the center of our galaxy, 30,000 light years away. It's just astonishing. At any rate, let's go on. The fourth property that we would like to know about stars is the physical size. How big the star is, how much space it takes up. Well, it turns out if we know temperature and luminosity, we can find the size. Okay? And that's because temperature tells you how bright the surface of the star is, and the luminosity tells you how bright the total star is. Well, those two things are related by the size of the star's surface. Okay. So, the surface brightness, or what your book calls energy flux, tells us how bright every square meter or every square mile or every square kilometer of the star is. And you can approximate that by something called the Stefan Boltzmann law. Okay, this is in your textbook. Basically, what it's telling you is the surface brightness depends on temperature to a very, very high power. So in other words, a little tiny tweak in temperature really, really increases the brightness of the surface tremendously, or decreases the brightness of the surface tremendously. So if you turn up the temperature just a tiny bit, the surface gets way, way brighter. If you double the temperature, the surface doesn't get twice as bright. It gets 2 to the 4th power, or 16 times as bright. If you cut the temperature in half, the surface doesn't get 1/2 as bright. It gets 1/16 as bright. And so the surface brightness of the star is very, very sensitive to temperature. This little thing here is called the Stefan Boltzmann constant. You probably won't ever have to actually use it, but it is just a constant that tells you how the units work out. Okay. Now, so the surface brightness depends only on the surface temperature, but the luminosity, the total brightness of the star, depends on how much surface you have and how bright that surface is. Okay. So let's do a little example here. Okay, so that means luminosity, before we do that example, that means luminosity is proportional to both the area and the surface brightness of the star. So let's have an example. Two stars with a surface temperature of around 6,000 degrees Kelvin. Okay. One happens to be our sun. Our sun has a surface temperature of approximately 6,000. It's actually closer to 5,800, but we're not going to split hairs. And then we have another star with the same surface temperature. Let's call it Capella, because there is a star called Capella, and it's about the same surface temperature as the sun. But it is much, much larger. Capella, or this star, this example star, is 100 times the luminosity of the sun. It's 100 times brighter. These little squares, if you blocked out the rest of the sun, except for this square, and you blocked out the rest of Capella, this other star, except for the little square, the light coming through this little square would be the same for both stars. Okay? But the total brightness of this star is as if you added up the brightness of all the little squares you would need to cover the surface, right? And the brightness of the sun would be, how many of these little squares would you have to multiply to get the total surface area of the sun times the brightness of one square? Well, clearly you would get way more brightness here than you would here. In other words, this star has 100 times the area, 100 times the number of squares than this star does. And that means it would have 10 times the radius. Okay. The big star is 100 times as luminous as the small star, the sun, so it must have 100 times the area of the small star. And since the area of a sphere, which is what a star shape is, the area of the sphere is proportional to the radius squared, what would you have to square to get 100? Well, you'd have to square 10. 10 times 10, or 10 squared, is 100. So the big star must be 10 times the radius or diameter of the sun. So in other words, you should be able to fit, and I probably didn't draw it quite properly here, but you should be able to fit 10 suns across the diameter of this star. Okay. A common everyday example of this, a campfire and a candle flame. A campfire and a candle flame have approximately the same temperature. But the reason a campfire gives off so much more energy and is so much hotter is because there's so much more of it. The surface area, the radiating surface area of the campfire is extremely large compared to that of the candle flame, even though they are both at approximately the same temperature. Okay, that is the end of part 4, and we will go on then to part 5.